Okay, so there are two different kinds of path integration. There's idiothetic or allothetic path integration. So idiothetic refers to self-generated information. So that would be counting of steps. So vestibular information, information from balance, information from rotation and motion in the body, proprioceptive feedback from limbs and muscles, and the motor output to limbs and muscles are all involved in idiothetic path integration. Really, all those points, what that means is just the movement in your own body, keeping track of the movement in your body. And then allothetic uses cues from the outside environment to estimate position. So an example here could be using optic flow, which we talked about. And there is some research with fiddler crabs showing they use the passive rotation of their surroundings to find a way to their nest. And that's a type of path integration. Most of the work on path integration you'll find is the first one, idiothetic. Okay. Right. So I mentioned this earlier, but by maintaining a record of distance and change the direction, an animal can actually calculate a vector back to where they started. So they have direction and distance, right? Okay. That's all we'll say on path integration, but I think it's pretty fascinating. Human beings can also use path integration. All right, so that's one form of orientation and navigation. Another really popular one is using landmarks. Probably pretty familiar with this, of course, but a lot of animals do it too. They also use landmarks. Objects that are fixed in space. They're reliable, they're always there, in their surrounding environment. So to demonstrate this, we'll talk about some classic work with the European bee wolf. So they're called bee wolves because they hunt bees. So you can see that here. This bee wolf hunting this bee, and then holding it to bring it back to its nest. The insect world is terrifying. All right. So, bee wolf goes out, finds a bee, delicious bee treat, wants to bring it back to its home, to its nest. And a pretty cool experiment. These researchers went out in the wild and found some bee wolves. They found where their nests were. And what they did was they put a bunch of pine cones around their nest. And they left them there for a while. And then what they did, after a while, was they moved the pine cones with the same orientation, the same configuration, over a little bit. Just next to the nest. And they wanted to see what the bee wolves would do. So you can see that demonstrated here. They move the pine cones over, see what the bee wolf does. Sure enough, it flies directly to the center of these pine cones. So that demonstrates that this animal is using the landmarks of pine cones to locate its nest, right? Locate the precise location of its nest. So that's a quite nice example of landmark use in animals. Of course, we use landmarks as well. So I said social science earlier, but you can think of really big landmarks like the CN Tower. How do we actually use landmarks to locate or to navigate? Well, they give us a bit of information, a bit of different information, right? They can give us direction information and distance information. How far you are from the landmark, where it is, in relation to you. That's important information. And it's reliable, right? The CN Tower doesn't just move around. Then it wouldn't be a very good landmark. And we talked about this already a little bit, but when you have direction and distance, it should say, not direction and direction. When you have both distance and direction, you have a vector. That helps you know where you're going. And this concept is pretty important in understanding triangulation. So when you can triangulate something, that really reduces errors when you're navigating. So if you have 3 landmarks, that'll certainly reduce any error. You can get good variance for 2 landmarks, or 1 even. But having 3 allows us to triangulate a location because we have more vectors. Here's another pretty classic experiment, and we're talking about migration again, okay? So, European starlings, okay? Their path for migration starts here and ends here, okay? So this long skinny arrow, that's the normal path. Birds start here, and they want to end up here. What some experimenters did was they went halfway through their path, right here, right? And they caught a bunch of starlings. Now some of them were juveniles, so some of them were young, and hadn't migrated before. So this is the first time they're migrating. And other starlings were older. So they've migrated multiple times, or at least once. What they did when they captured those starlings is they drove them across Europe and then released them. They had tags on them. Actually, it would have just been bands at that point. But basically, they tagged them so they knew who the individuals were. And then release them, okay? What ended up happening is that the juveniles didn't correct for the displacement. So they ended up basically just using vector navigation. They knew what direction they had to go in, and they kept going in that direction. And if you actually look at the vector, you can see it's almost like it's been cut and moved, right? But the experienced starlings didn't make those errors. They went straight to where they were supposed to go. And again, this would be known as true navigation. The findings from this paper showed that true navigation, then, depends on experience and memory, right? The juvenile starlings and the experienced starlings are using different systems to get where they're going. Okay. So what do you need for true navigation? Just like you would, if you didn't have nice apps that tell us where to go. You need a map, and you need a compass. That's a pretty important point in a lot of this work. To truly navigate, you need a sense of a map and a sense of a compass. So the juvenile starlings in this case, perhaps they have a compass to know what direction they're kind of going, right? But they certainly don't have both. So to truly navigate, like I said, this is kind of the best definition in my mind of navigation, is to have both a sense of location and a sense of direction, which I have neither. Some people, I'm sure, as you know, it could be anywhere and they know where north is, right? Some of us, perhaps not so much. But you need both of these to be able to navigate. All right. Okay, cognitive maps. So we talked about you need a map sense and a compass sense, right? So what is that map sense? And you might have heard the term cognitive map before. It's a pretty big concept in a lot of psychological research. But it's kind of hard to define, right? What really is a cognitive map? And how can we say if animals have a cognitive map or not? It's kind of tricky. One of the first researchers to discuss cognitive maps in rats and men, this is even before O'Keefe and Nadel. You might have heard of the hippocampus and cognitive map. Tolman found that rats that he was studying made novel shortcuts in his mazes. Sometimes they also escape their mazes, but they know where to go to get food rewards. So even though they're not in the maze, they escape the maze somehow, and they know directly where to go to find that food. And he said that rats and men, as well as men, have cognitive maps. And he defined that as representation of the environment, which indicates the routes, paths, and environmental relationships that an animal uses in making decisions about where to move. Okay. So, like I mentioned, after Tolman came out with this in 1948, O'Keefe and Nadel also discussed the hippocampus as a brain region for cognitive maps. That was in the 70s. Since then, there's been tons of research about cognitive maps, what they are, what animals have them, do animals have them. We still don't really have a nice, clear, beautiful answer for this question. Things got a little bit spicy when this guy Gould claimed honeybees have cognitive maps. And that's when some people were like, okay, hang on. So you're saying bees also have representation just like people. That seems like perhaps a bit of a stretch, right? And that led to this pretty important paper. So this work with bees, Gould saying bees have cognitive maps as well. Let me get back to this for a second. So Gould said bees have cognitive maps as well, because one of the important points that O'Keefe and Nagel made about cognitive maps is shortcuts. So taking a shortcut. Even if you haven't taken a path between two landmarks before, it's a novel path, making a shortcut is the key to a cognitive map. And Gould saw that his bees were doing this. They made novel shortcuts. And that's why he said bees have cognitive maps. Okay. We'll show a diagram for that in a minute too. But that led to this paper. Pretty good little short paper, if you're curious. Very nicely written. But basically Bennett's saying all of this work about animals having cognitive maps, he argues that no animal has been conclusively shown to have a cognitive map in terms of Tolman, O'Keefe, and Nagel's definitions, because there are simpler explanations of shortcutting available. And he basically says we should stop using the term. It's not helpful for understanding the spatial behavior of animals. Don't use it. We're going to use it. We've already used it. Sorry, Bennett. But I do see what he's saying. I think it's a really important point. Okay. And this is kind of demonstrating that shortcutting behavior, okay? So, this is from that same paper that I just showed. He's talking about the bees. That Gould says, oh, they have a cognitive map. Because they travel from one feeding point A to another feeding point B. Even though previously they hadn't done that before, okay? So basically, A and B feeding locations. Here's the hive. They frequently go to A, back to the hive. They frequently go to B, back to the hive. But from A to B, that's a shortcut. And Gould said that's evidence of a cognitive map. And Bennett is saying there are simpler explanations. Okay. So lots of text on this slide, but we've kind of already talked about a lot of this stuff. So the novel shortcut method, that's what we've just explained. It's a test for the use of a cognitive map, commonly used as a test for that. So the shortcut method test is whether an animal that has experience traveling from A to B and A to C can infer the spatial relation between B and C. But there are 3 different conditions, really, to be able to definitively say an animal has a cognitive map using the shortcut method. One of them is that the shortcut is actually novel. Now that's quite actually difficult to say about a wild animal that you're not observing constantly all the time since it was born, right? Can you definitively really say the shortcut is novel? Perhaps not. Another point is about the landmarks around A and B. So again, this is kind of in response to Gould's paper. And Bennett was saying, I'm going to go back for a second, that there are familiar landmarks in A and B that the animals could just see from A and B, clearly visible. Could they just be using landmarks? So the method requires proof that there are no landmarks at one site that are visible from the other site. You also have to rule out that path integration is not involved. So Bennett concluded in a review of all this previous research they had not, successfully agreed to these terms, really. So to be convincing, the novel shortcut. Oh wow, what's going on here? This is all shortcut. No test of contact. Clearly my text got messed up here. Seems to be a theme. But basically, all 3 alternatives have to be ruled out, and Bennett's saying, no, that hasn't happened in previous research. Alright, well, I'm going to re-upload this because this is so confusing. It's bothering me. So I'll re-upload the notes with the fixed version. Okay. Alright. Okay. Actually, with that, I think we're going to take a 15-minute break, and then we'll get back to Celestial Cube.